This is the second example for generating power from lecture 3.5. Okay, in this situation we have an automobile with a given mass, 1,650 kilograms, traveling up a slope that has a 7-degree angle from the horizontal at a constant rate of speed of 108 kilometers per hour. We're told to neglect any friction and drag, but we are told that the mechanical efficiency of just the drivetrain of the automobile is 0.65. So only 65% of the power being generated by the engine is actually going into making the car go up the hill. The other 35% is being lost internally to the car in friction between the gears and so forth. Okay, so we're asked to determine the required power output of the engine so that the car can go up this hill at this speed. Okay, so I'm going to draw a free body diagram of my car first so I can see which forces are acting on the car. That will then tell me what are the relevant work terms, and that's the work that goes into the power. Work divided by time, or the derivative of work with respect to time is power. Okay, so here's a free body diagram of my car. I'm going to put in a horizontal, vertical, XY coordinate system here. And I do know that there's an angle of 7 degrees here. So the forces acting on my car, there's going to be friction between the tires and the road, so F. And I'm just going to lump all the friction forces of all the wheels into one friction force here. There's going to be a weight force, mg. There's also going to be a normal force here. I can say that this angle here between the vertical and the normal force is 7 degrees. So here's my 7 degrees there. And I'm also going to put my velocity vector on here. So the car is moving in this direction. And so the question is now, which of these forces do work? So which of these forces do work, and hence which ones are going to be part of this power calculation? So which forces do work? Okay, so the first one we can think about is N. Well, N is perpendicular to the motion. N is perpendicular to the velocity. All right, if we write these as vectors, the normal force vector is perpendicular to the velocity vector, and so there's no work done. We have the friction force F. Again, we're going to assume here that the tires do not slip. We're not told that they slip, so I think that's a fair assumption. Assume tires do not slip. And so if the tires are not slipping, then this friction, the tire, when it's in the portion of the tire that's in contact with the road does not move. It does not move against the road. So as the tire rolls, different parts of the tire come into contact with the road, but none of those parts are slipping. So this friction force that I've drawn doesn't actually move. It's a static friction force. We'll talk more about rolling of wheels in our next module. But since the tires are not slipping, this friction force is not moving, so F does not move, and it does no work. The mg does move. It moves up the hill with the car, so mg does work, and so that's the only one of these forces that does work. We also know that the car is moving at constant velocity. So between any 2 points in time, the net work on the car is going to be 0 because its velocity is not changing, its kinetic energy is not changing. So what we could say is that the net work on the car over some time interval, over t interval, so an interval of time t, the net work has to be 0 because the velocity is constant. Well, we can say this is equal to the work of the weight force, and we know that's not going to be 0, but we need another term so that the net work comes out to be 0. And so this is going to be a generated work. This is the work that's done internal to the car, right? So they're in the cylinder of this engine, assuming it's an internal combustion engine, as the fuel is ignited and produces gaseous combustion products. Those gases push against the piston that then moves, and so that force on the piston that's moving is going to have a non-zero work associated with it, and so that's the work that the car is doing. That's where that work comes from. Okay. So our net work on the car is 0. It equals the work of the weight plus the work that's generated by the engine of the car. Now I'm really here interested in power, so I'm going to divide everything by time to get power terms. And so this is going to be then still 0 is going to equal the power associated with the mg force plus the power that's generated by the car, Pgen. So I can solve this for P generated. It's going to equal the negative power that's done by mg. And so remember, power, write this up here in green, power is equal to dot product of force and velocity. We can write this as the magnitude of the force times the magnitude of the velocity times the cosine of the angle between them. All right, so that's the equation we're going to use down here. So we're going to have negative, and the force of gravity is mg. The velocity of the car is given as v. Let's write that as v. And then we have to figure out the cosine of the angle between the mg force and the velocity. So I already know that the angle between mg and this normal force that I've drawn on the free body diagram is 7 degrees. I can then also say that this angle here between the normal force and the velocity, that's 90 degrees, because those are perpendicular to each other. So my total angle then between mg, which is pointing down, and velocity, which is pointing 7 degrees up the slope, that's going to be 97 degrees. So I'm going to have cosine of 97 degrees. And that is going to be a negative number. Cosine of 97 is negative, and that's going to cancel the negative out front. All right, so my power generated then is going to look like negative my mass, 1650 kilograms, times g, 9.81 meters per second squared, times my velocity, which was given as 108 kilometers per hour, but I need to convert that to meters per second. So I'm going to divide 1,000 meters by 1 kilometer and divide 1 hour by 3,600 seconds. And I end up with a velocity in meters per second. All right, so that's my velocity converted to meters per second. And then I have the cosine of 97 degrees. And if you work all that out, it comes out to a positive number, 59,180 watts. And so this is the power delivered by the drivetrain, power out of drivetrain. So if you think of our drivetrain up here, right, here's our drivetrain. We're going to have power in. This comes from the engine. Right, the engine is up here delivering power to the drivetrain, and then there's power out. And so we know that only 65% of the power delivered to the drivetrain comes out of it. The rest is lost to friction and noise and so forth. So if we want the power out of the engine, power out from the engine, it's going to be this 59,180 watts that we need to propel the car up the hill, divided by the efficiency, which is 0.65. This works out to 91,000 watts, which I'm going to write to 3 sig figs as 91.0 times 10 to the 3 watts. And that's my answer. It's about 120 horsepower, which seems like a reasonable number for most vehicles.